All right, we're going to keep talking about logarithms and go through 4 properties of logarithms. The first 3 we're going to kind of use together: the product rule, quotient rule, and power rule, and change of base property we'll go through at the end. All right, so here's the product rule. Okay, if you have the log of 2 things multiplied together, you can split them apart, but you need to add the 2 logs. So log base b of m times n equals log base b of m plus log base b of n. Okay, so for each of these properties, I'm going to just kind of go through and explain where they come from. You don't need to know this. You just need to be able to apply the product rule. Okay, but why does this work? All right, so let's start with this. We have log, so we're going to show this, right? We're going to show that log of m times n equals log of m plus log of n, where all the bases are the same. All right, so let little m equal this, and let big N, or little n, equal this. These are b's, log base b. So in exponential form, remember, this is b to the little n equals big N, and b to the little m equals big M. That's what this means, right? If we wrote that in exponential form. Okay? So we start with with the left side here, log base b of m times n. Okay? Well, we know that big M equals b to the m, and big N equals b to the b to the little n. Okay, so we just replaced m and n with that. Then we use properties of exponents, right? The same base, we can add the exponents together. And what does this mean? This is saying b to what power equals b to the m plus n? Well, the answer is m plus n. Okay. Well, m is log base b of m, and n is log base b of n. Okay, so you could take a minute just kind of reviewing that. But this property of logarithms comes from the property of exponents. Okay, so basically what we did was rewrite this in exponent form, use properties of exponents, and then rewrite it in log form. Okay, but like I said, that's just for your information. So how would we use this? Expand log base 3 of this expression. Okay, so what do we have multiplied together here? We've got this term, 3x plus 4. We can't break that apart anymore. We can't factor that. Times x times 30. Well, 30 has a bunch of factors, right? So that's the first thing we do is we factor 30. Okay, 2 times 3 times 5 times x times this factor, this linear factor that we can't factor anymore. And now we break this apart for each factor. Okay, it's going to be log base 3 of 2 plus log base 3 of 3 plus log base 3 of 5 plus log base 3 of x plus log base 3 of this whole thing. Now, this is an important thing to notice. Can we break this apart anymore? We cannot. We're not going to learn any properties. If you have log of one thing plus another, you cannot break it apart. It's just stuck, right? If we can't factor anything out of here, we can't break logs of sums apart. Okay, so this we just leave like that. I guess one last thing, we could simplify this perhaps just a little bit. What is this? Log base 3 of 3. This is saying 3 to what power equals 3? The answer is 1, right? So this term we could write as 1, just to simplify it a little bit more. All right, quotient rule is going to be very similar. I bet you could guess what it's going to be. If we have log base m of m minus n, m divided by n, instead of adding, we subtract, right? So again, let's just look real quick at where this comes from. So we're going to do a similar thing. We're going to show this property. So we're going to put it in exponential form, right? Exact same thing we did before. Little m is log base b of big M, same for n. So we could write these in exponential form like this. Okay, so log base b of m divided by n, let's replace big M and little n with b to the m and b to the n. Okay, now we use properties of exponents to write this as b to the m minus n. This is asking a question. B to what power equals b to the m plus m minus n power? The answer is m minus n. And now we put it back in log form. Okay, so what if we wanted to expand this whole expression? We've got things multiplied together, things divided, right? We have 15 times 5 times x minus 1 in these two terms. Well, first, let's just use the quotient rule, okay? We have log of this thing divided by this, so it's going to be log base 2 of this numerator minus log base 2 of the denominator, okay? So that's just using the quotient rule. And now can we break this up anymore? Yes, we can. We've got a bunch of things multiplied together, 3 times 5 times x minus 1. And here we've got this times this. So I know this print is a little bit small, but we can break this up, right? This is going to be log times 3 plus log times 5 plus log times x minus 1 minus log of this factor plus log of that factor. And then we just distribute the minus sign to each of these two terms. Okay, so this looks super long and scary. Okay, we've just taken log of the numerator minus log of the denominator and then broken it up with the product rule. All right, the power rule. This is powerful. If you have log base b of m to some power n, look what you can do. You can pop that exponent out front. You just take it off here and put it out front. Okay, we're going to use this a lot. So let's see why this would work. This is kind of just gives you some intuition. It's not a full proof, right? But if we had log of x squared, that's the same as log base b of x times x. We can use the power or the product rule to break that up. And look, we've got two of them, right? So it's not really a proof, but it gives you an idea of why this would work, right? If we have an exponent here, we can use the product rule to make it a sum. And the number of things we're summing together is going to be the exponent, which is also going to be the coefficient of that term if we used the product rule. So we're going to use things like 100 is 10 squared, or square root of 3 is 3 to the 1/2. 1 over e is e to the negative 1, right? So we're going to use properties like this of exponents to rewrite things to have exponents. So so here's the application, log base 2 of x to the 5th. Here's the exponent. We can just bring that out front. That's all we have to do. Expand log base 3 of 25. Well, we could do this two ways. We could think of this as 5 times 5 and use the product rule. We could think of this as 5 squared and use the power rule. Either way is fine. Okay, now we could do this the other way. If we have a coefficient in front of a log for natural log of x, and we want to have a leading coefficient of 1, well, we can move this coefficient to be an exponent of the thing we're taking the log of. Okay. All right, so let's rewrite this as a sum or difference of logs. Let's expand this as much as we can. Well, let's see, we're going to probably use the quotient rule, we're going to use the power rule, and we're going to use, the product rule and the power rule. So first thing, let's use the quotient rule, right? It's going to be natural log of the numerator minus natural log of the denominator. So notice, to this point, we have not paid any attention to what base our log is, right? It could be log base 2, log base 7, log base e, natural log, right? Whatever the base is, that's what we stay with. Okay, so we're starting with natural logs. We're just sticking with natural logs. All right, now let's use the product rule and expand this, right? We can break this apart as natural log of x to the 4th plus natural log of y. And now the last thing we're going to do is use the power rule to just bring that 4 out front, right? 4 natural log of x plus natural log of y minus natural log of 7. So we've done it. We've broken this apart as much as we can. We've expanded this logarithm. Let's expand this. Well, the first thing we're going to need to recognize is that square root of x is the same as x to the 1/2, right? And then once we have that, we can use the power rule and bring it out front. Expand this. Okay, again, this is going to look complicated, but we're just using those 3 rules. We've got a quotient, so we're going to have this minus this. Then we're going to break apart all of the things we're multiplying together using the product rule. And then probably at the end, we're going to use the power rule to bring this 3 out in front. All right, So, quotient rule. Well, they kind of did the quotient rule and the product rule all in one, right? They broke up, they said log of 64 plus log of x cubed plus log of this thing minus log of the denominator. Okay, so hopefully that's kind of combining those steps is making sense. All right, well, what can we break up here? So now they were a little bit clever, and they rewrote 64 as 2 to the 6th power. Okay, and now they can bring that 6 out front. Here we had x cubed, they brought the 3 out front. And these, can we break these up anymore? We cannot, right? 4x plus 1, 2x minus 1, they are stuck. It looks like maybe there should be some way we could break them up, but there's not. Okay, now let's go the other direction. We've been expanding logarithms. Now let's condense them. So let's combine logarithms. So the important thing here is that they all have the same base, right? Log base 3, log base 3, log base 3. That has to be the case. So it's going to be these two things multiplied together, 5 and 8 multiplied together, and then divided by 2, right? So we just look at the first two terms and combine them, right? Log of 5, log of 8, we multiply 5 times 8 to get log of 40. And now we're going to have log of 40 minus log base 3 of 2. And now we're going to use the quotient rule. Log of 40 divided by 2, which gives us log base 3 of 20. Okay. Let's condense this. All right, first thing, let's look. We've got log base 2's. That's good. We need the same bases to be able to combine them. But we do have some coefficients, right? Having coefficients out front makes it so that we can't combine log terms. So how do we get rid of those coefficients? We bring them into the exponents. So let's do that. That's the first thing we do. Log base 2 of x squared stays the same. This becomes a square root of this term, square root of x minus 1, right? We bring that as an exponent and write it as square root. You have to write it as square root. You could keep it as an exponent to the 1/2. X plus 3, we're going to bring this 3 up, right? That's squared. We bring the 3 up. We multiply those exponents together to get 6. Okay, so now we've got log base 2's with no coefficients. So now we can use the product rule to combine these and the quotient rule to divide by that. So to combine these, we just get x squared times square root of x minus 1 minus this thing. And I did not move my mouse so you can see. Now we just use the quotient rule in the last step. Yep, so that's combined. Let's do another one. Okay, this is going to be similar. If we have a log, we have common logs, right? Log base 10 in all three terms, but we've got these exponents. So we're going to have to move these, not exponents, sorry, coefficients. We're going to need to move the coefficients to become exponents. So this x becomes x squared right here. This becomes x plus 5 to the 4th right here. And this becomes 3x plus 5 to the 1 over x, or x to the minus 1 power. Okay. Now this is going to be a little bit tricky. How are we going to combine these? We have this plus this. Okay, so we use the product rule to combine those two terms. And now we've got this log minus that log. And we get this term. Okay, using the quotient rule. All right, here's an application. So here's a definition. In chemistry, pH is defined by this. You've probably heard of the pH balance of, lemon juice is acidic and soap is basic. So here's what that means, okay? This is H plus means the concentration of hydrogen ions. Okay, hydrogen ions in a mixture or in a chemical is the concentration of those hydrogen ions is what we take. We take the log of that concentration. The minus of the log of that concentration tells us the pH of something. So they say if the concentration in a liquid is doubled, what happens to the pH? So if this concentration doubles, what happens? Well, so here's our original concentration, let's say, is C. So if we double that concentration, how can we simplify this? Well, we could say this is minus log of 2 plus log of C, right? And then we could distribute the minus sign. So minus log of 2. So our original pH would be minus log of C, right? If that was our original concentration, that would be our original pH. Let's call that P. So our new pH is going to be P, let's call this P, minus log of 2. So P minus log of 2, we put that in our calculator, and we get that value. So, doubling the hydrogen concentration decreases our pH by 0.3. All right, the last property we're going to talk about, the change of base formula. Okay. This is really, really useful. What this means is, suppose we have like a log base anything, okay, like log base 2 or 7 or something. We get to choose a new base, n, okay? And this is going to be equal to log base n of m divided by log base n of b. So m and b are numbers that are given to us in our original expression. We choose n. Okay, we can choose any number we want for n. Okay, well, it can't be 1. Okay, anything but 1. Okay. Now, we can choose anything we want, but the numbers we are going to choose are going to be log base 10. We're going to let n equal 10, or log base e. Okay. So this is saying like log base b of m is natural log of m divided by natural log of b, or common log. We could use common log of m divided by common log of b. Why would we do that? Because we have buttons on our calculator with those bases. So let's just, again, we'll just run through why this works, and then we'll do examples of practicing it. So we're going to create a variable y that's our original log expression, log base b of m. Okay. So in exponential form, b to the y equals m. Here we go. So let's replace m with b to the y. Okay. This says apply the one-to-one property. What does that mean? That means if we have a log function, if two things are equal, then we know that their insides are equal. Or if their insides are equal, we know that log of those numbers is equal, because log is a one-to-one function. Okay, so now we're going to use the exponent property, or the power property, bring y out front. Okay. So now we divide. We say y equals log base n of m divided by log base n of b. Well, what is y? Y is log base b of m. Okay. So that's where this comes from. Again, we're just going to use it. We're not going to ask you to recreate that sort of proof of why it works. All right, so here's why we'd use this. What if I said, what is log base 5 of 3? How do you solve it? I mean, we don't have a log base 5 button on our calculator, right? We have to change this to be in terms, if we wanted like a decimal approximation to this, we have to change this to be in terms of things we can use our calculator for. So we just choose a new base, e, and we say, okay, log base e of 3, this is equal to log base e of 3 divided by log base e of 5, or natural log of 3 divided by natural log of 5. And that we could just put in our calculator, right? Natural log of 3 divided by natural log of 5. I don't know what it is, but we could find that answer. What if we want to do this? Evaluate log base 2 of 10. Well, this is saying 2 to what power equals 10? I don't know, like something a little bit more than 3 and less than 4, right? We could think 2 to what power is 10? Well, 2 cubed is 9, or is 8. 2 to the 4th is 16. So something between those. But that's really as close as we can get without using the change of base. Right? So let's take the natural log of 10 divided by the natural log of 2 using the change of base formula, and we put this in our calculator. What happens if we instead chose log base 10 of 10 divided by log base 10 of 2? Put that in your calculator, you'll get the exact same number. It does not matter. You just choose your favorite log base and go with it. And yeah, that's the end of this section. So those are the 4 log properties. You get lots of practice in your homework applying them. We're going to be expanding log expressions, condensing log expressions, or evaluating logs using the change of base formula.